Welcome to Web Handling. My name is Dave Roysum. What could be more common in the web handling world than webs going over rollers? In this module, we will assemble several components of well-established web handling know-how in a brand new way. We will create a single, simple, and safe design methodology to protect our customer, the web, from the combined damage of several insults. In the Greek world, there were four elementals, earth, wind, fire, and water, from which all matter could be made by combinations in various proportions. In our machine world of webs going over rollers, we have a half-dozen elements that stress the web. Until now, they have usually only been combined one or at most two at a time. Perhaps the most widely modeled and measured, such as via load cells, is the variation of MD tension with time. However, the MD tension will also vary down through a drive zone due to mechanical factors such as roller bearing drag and roller inertia. Though we seldom have a second load cell to actually measure this down web tension profile, the calculations are easy. Even so, the load cell roller only gives us an average across the width. We know that tension has a profile variation across the width caused by in-plane roller misalignment. No less important is the perennial headache, the baggy web. This also contributes to variation across the width. Finally, with thick webs, we have two factors that can cause a variation through the thickness. These are bending over a roller and curl. In summary, we have variations with respect to time and variations with respect to down web position. We also have two sources of variation across the width and two sources of variation with respect to thickness. Our challenge will be to put all of these together in a meaningful way. A major limitation until now was that these elements were considered separately, or at most a couple at a time. This could result in non-conservative design if other significant sources are not considered. It could also, paradoxically, result in over-conservative design if unnecessarily large safety factors for nominal tension settings are used, in lieu of considering all of the elements for an individual case. In short, to be safe, but not too safe, we must consider all common stress contributions. To be useful, the procedure must be easy to understand, and the inputs must be easy to obtain. However, to be really useful, we would want a well-tested app so that every potential user would not have to make and test their own calculation model. A simple and safe model for how we will proceed is similar to how we learned how to handle stress concentrations, such as resulting from a tensile specimen with a central hole. As seen here, the peak MD tension on the side of the hole is the nominal tension times the stress concentration factor. This factor can be obtained from calculation or from a graph. This example for a pin in a hole is one of many that can be found in design textbooks. In some sense, this is already implicitly done when selecting the upper end of a tension range that might be a safe setting on a web machine. The widely quoted tensioning of 10 to 25% of MD tensile strength works well for most situations, even though there are exceptions such as crepe tissue, which can be safely pulled up to nearly 50% of its yield tension. Here, we will note for this common starting point guideline, we are in effect running a safety factor of 4 on yield. This safety factor is largely to account for a web and a machine that are less than perfect, such as due to the elements we have already listed. If the web and world were perfect, there would be no need to limit tension to such conservative values for web handling purposes. Also, we should note that the critical direction that we will consider is in the MD. This is a great convenience not having to mess with Moore's circle. drive controls do not hold tensions perfectly. Some of this is inherent in the unavoidable following errors for PID controls. To this, we add many other sources of variations, including a less than optimally designed or tuned drive system. An often quoted drive quality standard is to hold tensions, as measured by responsive load cells, to within 5% of set point during steady state, 10% during speed changes, and perhaps a bit more due to violent short events such as the turret index. If we use the stress multiplier concept for this example, the value would be 1.1. Most real drive systems can achieve this without inordinate cost, though you do need to take some care in the details. Depending on where in the design process you are when using this methodology, the user would select a value for the allowable variation as determined by a target specification, a performance specification such as written in a contract, or what was actually measured on the machine. Tensions measured at a load cell define tension only at that roller. Tension on the roller just upstream and just downstream will be different, even if they are all in the same drive zone. At steady state, this is largely caused by roller bearing drag. Also, this downweb tension profile will be different during acceleration, run, and deceleration. This additional contribution during speed changes is due to roller inertia. In my Mechanics of Rollers book, I suggest a starting point guideline of no more than a 10% rise of tension in a drive zone due to roller bearing drag and inertia. Using the stress multiplier concept, the value would be 1.1 for this example. For lightweight webs, we may open this up a bit, as this value may be an unaffordable luxury for some. As an aside, Ron Lynch has done much marvelous modeling and teaching that expands on these issues to also include checking every roller for loss of traction. Bearing drag, inertia, and loss of traction are especially important issues for lightweight webs. I think one of the most useful things that Dr. John Shelton has ever done was to show us how to calculate the tension profile caused by the movement of a steering guide roller. However, at that time, 1965, I do not believe he was thinking at all of the much more general application of in-plane roller misalignment. In 1986, I detailed this new use of John's old formula in my roller book. In 2013, I wrote extensively on alignment. Also in 2013, we made this alignment design and maintenance equation accessible to almost anyone with two thumbs as one of the first of the Abbott apps. Because of John, we can easily calculate the stress multiplier at the upstream roller. While this is often called a slack web criteria, we are more interested here in the outside of the bend where the local tension rises. We will call this stress multiplier F sub m. Baggy webs are much tougher to quantify. In fact, severity has all been impossible to measure regularly, as one might wish to do, such as for quality control purposes. However, just because it is tough does not mean that we can ignore its contribution. We will designate the Baggy Web stress multiplier as F sub b. It is the ratio of the peak MD tension over the average tension. This has been measured on a contract study basis by labs such as the Web Handling Research Center and FP Innovations. It is found to vary in the range of perhaps 1.1 to more than 2. Measurement on commercial machines has also been done in paper, film, and metal industries, though the efforts are exceedingly rare and the results have not been replicated and reported in publications. Two potential problems are unique to thick webs. We present the first one here, and that is roller bend radius. The strain multiplier is easily calculated from geometry. For this element, the MD tension variation is through the thickness. The second of the thick web considerations is curl that might come from manufacturing or roll set. Again, the calculations for the strain multiplier is easily calculated from measured curl. In 2006, Dr. Ron Swanson gave us a truly wonderful survey of the good, the bad, and the ugly of curl measurements. Before we can calculate an overall safety factor, we need to do 3 final checks. Are the primary stresses in the machine direction? Could the elements align in space? And could the elements align in time? In the white paper, we discuss how all of these components could indeed conspire to trouble a particular local spot on the web. In the white paper, you will find the equation elements, definitions, and derivations. The safety factor is calculated from our 6 stress multipliers as we have just discussed. To these, we add inputs for the material yield stress and modulus, as well as the strains due to the simple web tensioning, curl, and bend radius. Application could begin with a known marginal condition, from which the current safety factor could be calculated. Once this so-called threshold of pain is obtained, we are free to allocate our precision budget in different ways. If, for example, drives are difficult, we could open up that tolerance and make up with a more precise roller alignment. If we have increasing baggy webs, we might counter with a combination of both improved drives and improved mechanicals. With experience, we may move into new applications solely based on what safety factor has been found to be a good compromise between over and under design. Let me offer a few general observations, beginning with an industry I know best, paper. Here, we might at most run a simple web tension setting of 1/4 of the breaking strength. However, the true safety factor is not as high, perhaps more like 3, due to occasional mild bagginess and just a tiny smidge of drive system imperfections. Misalignment and thick web concerns are truly negligible. The concern driving this generous true safety factor in paper is to reduce the incidence of web breaks, though already quite rare, because these tension-dependent problems are costly. In tissue, on the other hand, the nominal web tension setting may be as much as 1/2 of yield. Here, the true safety factor is reduced to a very small 1.5 and is mostly due to the possibility of large bagginess. Here, big safety factors are not needed, as the penalty for overstressing a local area is merely pulling a bit of crepe out, an already regular event anyway. In film and other converting, we run tensions perhaps slightly less than the norm, perhaps as much as 1/5 of yield. However, the true safety factor is greatly reduced due to rampant misalignment and quite possibly large bagginess. What is most important to you is your web and your machine. With just a quick look at a known marginal situation in your plant, you can determine a safety factor that is appropriate for you. As they say, your mileage may vary. However, before we get too excited, we should also honestly list some of the more flagrant limitations, besides the obvious challenges of getting some of the inputs, such as the Baggy Web stress multiplier. First, this approach is slightly conservative because it assumes that all elements not only could, but in fact do align on a particular spot on the web. We also simplify the problem so that anisotropy and nonlinearities do not have to be considered. Finally, and perhaps most limiting, is that the web cannot go slack anywhere, which would also violate linearity. Still, there is much to be said about a method that is simple. Reducing assumptions and generalizations may be something to consider for future work, though this will almost certainly take it out of the hands of our most common customer, the casual industrial practitioner. Thank you so very much for your time and allowing my avatar to present this material for me. Though it is always difficult to make predictions, I believe that this was one of the more generally useful concepts that I've developed in recent years. I hope that you find inspiration and application from these ideas. Thank you and have a good conference.